All right, last live stream of the summer semester. Now, I do have questions from email, but before I get to the email, just want to remind everyone everything is due tonight at midnight. So, all the labs, all the homeworks, all the lab notebooks, everything is due today. The goal tomorrow is to get up, compile all of it, and get your lab grades in, get your homework grades in, and get everything posted to Blackboard. So, the only outstanding grades you have over the weekend is going to be the final exam. Remember, the final exam is on Blackboard. You get an hour and 50 minutes to take it. 35 questions, multiple choice. Multiple choice answers do have their own partial credit. I do plan on looking through your responses to make sure that it's grading it correctly. I am inclined to agree with this final exam that's been given before in terms of the partial credit, but you've also got a link to upload your work as well if you like to do that. Do upload your work. It sends me a message about that, so you'll know that I've looked over your final exam. And once you submit your final exam, you'll have a pretty good idea of what your grade is in the course. Now, Monday, not going to be really hearing out many requests for grade changes or requests if you can get a grade boost. The big reason is that by Monday at 5 p.m., it's the close of business day. I need to submit my grades right after that to make sure that they get through the system. So Tuesday morning at 10 a.m., my grades have to be finalized and they have to be submitted. So basically, I'm using Monday to make sure that everything's ready to go, so this way there's no issues with getting your grades submitted for your transcripts. Now, if you take the exam like tomorrow or Saturday, you send me an email, I might have some time to go back and forth and maybe take a look at your grades. But again, as of Monday, the grade you get is the grade you get. We as a class don't have time to really do anything that late, that close to the deadlines. So I did have a request today for 3 different questions. Nernst, half-life, and the conversion between voltage and free energy. So let me bring up voltage and free energy. I'll share my desktop with you really quick. So questions like this: if the free energy of a reaction is minus 148.2 kilojoules per mole, what is the voltage if 2 electrons are transferred? At the free energy, and then you've got the other one, what is the voltage, and so forth. So these types of problems are solved using the same formula. This is actually where the Nernst equation comes from. So earlier in the semester, we had this delta G equals delta G naught plus RT ln of Q. And if you multiply this by minus 1 over NF, you get E equals E naught minus RT over NF ln of Q. So this is where the Nernst equation comes from. It comes from taking that Gibbs equation we had on test 3 and switching from kilojoules to mole to volts per electron equivalent. So we have a definition that voltage equals minus delta G over NF, and we can rearrange this to get minus NF times E equals delta G. So for all of these types of problems, you're just going to solve for the unknown variable. Now, you're going to have to be given numbers of electrons if you're not given a reaction. So if you look at the first problem on that homework set, it says the free energy change, delta G, is minus 148.2. And there are 2 electrons transferred, and it's asking you what is the voltage, what's E. F here is Faraday's constant, 96.485. Some books do publish 96,485. The big issue with that's joules per volt electron. It's a weird conversion factor. I never saw it when I was practicing electrochem. It's basically because some instructors teach joules per mole Kelvin with their delta H's and delta G's. You need to be working with kilojoules per mole. So if delta G is in kilojoules per mole, your Faraday's constant is 96.485. Basically, you're either going to be solving for the voltage or the delta G, but it's just that relationship. Now, the other question, 2 other questions. One about half-life. And I'll bring up those homeworks so you can see an example of that. What is the half-life of oxygen 19 if only 22.3 grams of a 25.6 gram sample is left after 5.23 seconds? For these types of questions, the formula you're going to use the actual formula is N equals N naught 1/2 to the T over T sub 1/2. This is not T times 1/2. It is T with a subscript 1/2 to indicate that it is half-life. In here can be any number that can be connected back to atoms. So it can be atoms, it can be moles, it can be grams. It doesn't matter so long as N and N naught have the same units. Now, we can rearrange this equation by dividing N over N naught taking the natural log or the logarithm, honestly, both work. Doesn't really change anything in terms of your final answer. Natural log is just the more natural logarithm to work with. Dividing this by the ln of 1/2, and this gives us t over t 1/2. So this is the same formula, it's just been rearranged. To solve for an unknown variable, just plug in all the numbers you have. So in the case of the first problem, go back to the desktop. You've got 22.3 grams that remain. You started out with 25.6, and the time was 5.23 seconds. The only challenge here is solving for t 1/2 if it's in the denominator, and that challenge is just algebra. So we can just bring the t 1/2 over, divide this whole number over. So we get 5.23 divided by whatever that number is, equals the half-life time. Now the other question was finding the reference potential based off of for the Nernst equation. Brought the wrong one. Just a minute. So the other types of problems are finding, the question was asked, how do you find these reference or these standard voltages? To do this, you need to identify the oxidation and reduction reactions. And so what you're going to do to find E0 of the cell is the reduction potential of the reduction reaction and the reaction minus what you find in the table for the oxidation. Now the oxidation reaction is going to be written backwards from the way you see it in the table. There are 2 tables online for the homework. The 2 tables, tables of standard reduction potentials. This is a PDF. This is going to have every single one. The one you're going to be given on the exam, this final exam formula sheet, has a simplified version of these. It may not contain what you need for the homework, but this was just so I could have more options in terms of doing the homework. Give it just a minute to load. There are 2 tables by voltage and by, I should say by the reductant, whatever is being reduced. So let's say we had this reaction, and I'll write it up on the board really quick. So we had silver plus 2, or silver plus 1, plus aluminum, going back and forth to 3 silver, plus aluminum plus 3, and I've got the reaction of aluminum plus 3, plus 3 electrons, going to minus 1.66 volts, sorry, going to aluminum, it's minus 1.66 volts, and the other reaction, silver plus 1, plus an electron, going to silver at 0.8 volts. So if my reaction here was 3 silver plus 1 plus aluminum goes back and forth to 3 silver plus 1 plus 3, the voltage of such a cell is the reduction reaction. In this case, it's silver going from plus 1 to 0. So that would be 0.80 volts, minus the voltage of aluminum going to aluminum plus 3, which is minus 1.66 volts. Keep in mind you're subtracting a negative here. That does happen with these reference potentials. So that gives you 2.46 volts. Now, a mistake I occasionally see, you don't have to multiply by this 3. These reduction potentials are all normalized on a per electron basis. So if you triple the reaction, you triple the voltage, or you're going to triple the free energy, which in turn will triple the number of electrons. So we had that relationship from before. E equals negative delta G over NF. If we triple this reaction, we triple the delta G, but we also triple number of electrons. So this ends up working out. We don't ever have to scale our half reactions to match up with what we see in the reaction itself. All right, now to the chat questions. When you have time, you can go over number 4 on the redox lab. So the reaction is permanganate, MnO4, plus chloride goes to MnO2 plus chlorate, and it's asking you to balance the reaction. First thing you have to do is figure out oxidation states. For permanganese, it's +7 to +4. For chloride, it's -1 to +5. So if we break this into 2 half reactions, we have MnO4 -1 goes to MnO2. We have a charge change from +7 to +4. That's 3 electrons. Wait. Yeah, that's 3 electrons. But keep in mind that we've got 1 manganese atom doing it, so this will give us 3 electrons on the left. For chlorine, it goes from -1 +5. We have 6 electrons, and there's 1 chlorine atom doing it, so this gives us an end result of 6 electrons. We want to be able to add the 2 half reactions together in such a way that these electrons cancel out. So if we double this reaction, we get 6 electrons, 2, and 2. Our 6 electrons cancel out, and we get 2 MnO4 plus chloride goes to 2 MnO2 plus ClO3. Now, the thing to keep beyond this, you're just balancing with water and H plus to convert from basic conditions. Well, talk about to convert to basic conditions. I'll leave it up to you to balance the oxygens and the hydrogens. That's pretty trivial. You're just going to add water and hydrogen. But let's say for whatever reason you ended up getting 2H plus and H2O. And again, I don't know if this is how it balanced. I would rather you work through that on your own. But let's say this is what you ended with. To switch this to basic conditions, first step, for every H plus you see on one side, add an OH minus on the other side. So we have our 2 H pluses, we're going to get 2 hydroxides. Convert your H pluses to waters. And then cancel out any water that appears on both sides. So we've got one on the right, one on the left, and this is how we would balance out. Again, assuming that's what you start with, I just kind of made that up. But I'll leave balancing from here forward up to you. All right. Next question. If a body center cubic crystal is composed of atoms that have an atomic weight of 203.2 mu and atomic radius of 0.225 nanometer, then what is the theoretical density in grams per centimeters cubed? So there is a formula sheet that you'll be given on the exam, and I'll bring it back up. All right. Actually, it's right here. So it's one of these 3 formulas, and you're given our bracket here to be nanometers. So if your radius is in nanometers, that's just going to be what you stick in here. You just have to remember which is which, and since the final exam is open notes, you can definitely go back to the test 1 notes and look it up. So which structure were you looking at? You were looking at BCC. So body-centered cubic has the 2 on top. So it'll be this formula. To calculate the theoretical density, you just plug everything in. Make a little bit of space here. So our rho, our density, is 2 divided by 16 divided by 3 times the radius to the 2nd power. All of that to the 3/2 power. times the molecular weight divided by 602. So if I use the numbers that you've given me, 0.25225, and molecular weight of 203.2, I get a density of 4.81. So those types of questions are just very much plug and chug. Just use the formulas. Again, you know what the formula sheet is going to be for the final. I've given it to you. So if you want to write out which of these corresponds to primitive, BCC, and FCC, you're free to do so. Other questions? No other questions? Let's hope that wire is important. wonder if that's the ground. That would make a lot of sense, actually. Grams of an unknown. Hold on. Check one thing before I answer your question. So 10 grams of onion salt dissolved in 500 grams of acetic acid. Change the boiling point by 0.651 degrees. What is the molecular weight of the unknown solute? So this is going to go back to test 1. So you got your relationship delta T equals K IM. In this case, we're looking at a boiling point. So this is KB. And we know that molarity is moles per kilogram of solvent. And that moles times molecular weight equals our grams of solute. So we can start rearranging these two relationships. Molecular weight equals the grams divided by the moles. The molality is equal to the moles. Oh, sorry, solve for moles. So moles equals grams over molecular weight. So molality equals moles, which in this case is grams over molecular weight, times the kilograms of solvents. And we can just plug into there. So what you do for these types of problems is use that delta T formula to solve for the molality, use the mass of solvent to give you the moles of solute, and then use the molecular weight, figure out the molecular weight from the grams that were dissolved divided by the moles that you figured out using the delta T equation. KB, you have to look it up in a table. So if you go to the course website, you're also going to find this on, hold on, let me bring it up. So if you go to that final exam worksheet, you reopen it. And this can also be found in the test 1 material as well. Assuming it loads at some point. But yeah, these are tables and you would be given these values. I'm just trying to get the tables to load. So we've hit the part of the live stream where this laptop likes to crash. So in the formula sheet, there's the physical properties of the solvent, there's your Kf and your Kv. So those will be provided to you. Other questions? Correct. So the final exam is more of a summary of what was on test 1, 2, 3, 4, and the new material. So the questions aren't nearly as in depth, but you've definitely seen the concepts before. So you haven't necessarily seen the questions themselves, but the concepts are definitely tested on the final exam. So I put that caveat there in to say that you're not going to see like verbatim questions taken off, but the concepts are going to be on there. There's not going to be any concepts that are completely new that we didn't assess. I would recommend it also just go through the homework again, making sure that you're understanding the bigger picture. So in terms of the final exam, if you open up the syllabus, there's about 38, 39 statements about the concepts that are covered in the class. Those are all being assessed on this final exam. So if you open up the syllabus and go through the course objectives, those are the types of information that you're demonstrating understanding of on the final exam. So if you look at those concepts and you can say, I can solve a problem like this, I can solve a problem like this, you're going to be fine. But again, there's really nothing. The questions themselves are much easier in terms of workloads versus the questions I would normally ask on exam, simply because it's more diverse. There's more knowledge-based questions on this exam, on the final exam. There's typically, I think, roughly 10 knowledge-based questions of the 35, which is more than I normally give for like an exam itself. So yeah, I would say go back through, look through the packets. There's a review packet on the course website as well for the final exam. It trims out a lot of, it should trim out a lot of the dead weight that I tested more in depth on during the regular exam. But yeah, that's what I would recommend, is going through the packets and using those. I would recommend going back through the test one packet first. It would surprise you how much material we've actually covered this semester. And it's kind of like that retroactive thing that what we covered at the beginning of the semester you've forgotten because it was so far away. So yeah, go back through and make sure you can do the qualitative stuff on the first exam as well. You're welcome. Any other questions? All right, if that's it, we'll call it for today. Again, shoot me emails. I will try. I'm gonna try to be as accessible as I can this weekend. But again, go ahead and start taking the final exams. Remember, everything is due tonight. So after midnight tonight, the only thing you should have left to do for this class is the final exam. All right, good luck.